Let's suppose that we have a 3-node network with the costs on the edges as shown. Initially, each node has a single distance vector representing the shortest path cost to each other incident node in the graph. For example, the distance between x and x is obviously 0, and the shortest known distance between x and y from x's perspective is 1, the direct path. Similarly, the shortest known distance between x and z to x at the outset is 5, because all it knows is the direct path. Note that a shorter path between x and z exists via y, but x simply doesn't know about it yet. Now, in distance vector routing, every node sends its vectors to every other adjacent node, and each node then updates its routing table according to the Bellman-Ford equation. Let's look at what happens when node x learns of y's distance vectors. Well, in this case, the distance from x to z will be computed as the minimum of the sums of all distances to z through any intermediate node. So the cost between x and y is 1, and the distance between y and z, as discovered by y's distance vector, is 2. Therefore, x can update its shortest cost distance to z as 3. Similarly, x will receive a distance vector from z, 520, but of course, when it uses the Bellman-Ford equation to update its distances, again, the distance between z and x will be updated from 5 to 3. We can repeat this exercise at other nodes as they receive distance vectors from other nodes in the topology, and quickly every node in the network has a complete routing table. Now, when costs decrease, the network converges quickly. But one problem is that when failures occur, bad news can actually travel slowly.